All right. So everyone can see my screen, okay?
Yes, please go ahead.
Cool. Yeah, so hello everyone. So glad to be here. Yeah, so I graduated from Stanford 2 years ago, and so since then I've been a founding member of this AI software startup based in Silicon Valley, AIZip. So today I'm actually gonna sort of rewind my memory a little bit and talk about this paper that we published in Nature about 2 years ago. And this paper is about a RAM computing memory chip that can provide efficient, versatile, and accurate AI inference. So I guess towards this group of audience, I probably don't need to say too much about, what is computing memory and why it is important, right? But the goal really is to minimize the data movement between separate memory and compute units, which dominates both energy consumption and latency in most of the AI systems today. So there has been a lot of efforts in both the industry and in academia of designing this specialized AI accelerator chips, right? So these chips has more fine-grained and distributed memory hierarchy, such that the compute can be distributed, and so they will stay closer to where the data is. And people typically call this near memory computing paradigm. And really, to the end of this path, we're looking at an architecture where compute and memory co-locate at the same place, right? And in the context of deep neural network, it essentially means that all the neural network weights will be stored inside a memory, and so during the inference, you will no longer need to fetch this weight from an external RAM, right? So that the data movement can really be minimized. What it takes to really get there, right? So first of all, this memory needs to offer enough density and capacity in order to store all the model weights, right? And so this means, for some of the smallest tiny ML models, which my current company has been working on. So this means 100 kilobytes of RAM, right? But then for let's say today's language models, right? Even the smallest one that can deliver a reasonably good performance will need gigabytes of memory, right? So that's quite some memory capacity requirements. And then the memory and logic devices also need to be integrated monolithically into a single chip, right? And this is because this memory array will need to be operated by some peripheral circuits that will need to use the logic device. And also, this computing memory array is not going to be the only thing on the chip. It will also be communicating with other blocks that will also be implemented using these logic devices on the same chip. And finally, this computing memory array should support very energy efficient in-memory computation. Right. So apparently there are many different memory technologies that can be used to implement computing memory. But among them, I think this RRAM or resistive switching random access memory is a candidate that can potentially in the future check all the three check marks, right? So here's just some basics about RRAM. So it is a two-terminal non-volatile memory devices, and it consists of a metal oxide sandwiched by two metal electrodes. It stores information using resistance, and it can be toggled in between a high and a low states, and actually many intermediate states in between by applying electric field across the electrodes, right? And importantly, these RRAM devices can be fabricated directly on top of the CMOS, right? So it can be easily embedded into a logic chip. So, today's RRAM devices are still quite limited in capacity. But, going into the future, we do think this RRAM device has great potential to scale, right? And this scaling gonna happen in these 4 dimensions, and we like to call it X, Y, Z, and M, right? So X and Y essentially stands for these two-dimensional planar downscaling. And Z stands for scaling 3D along the vertical axis, just like a NAND flash array. And there actually has been several experimental demonstration of this vertical RRAM array that is very, very dense, right? And finally, this RRAM cell can store multiple bits. And so these three scaling together will enable RRAM to, has a potential to really go into 100 megabytes or even gigabytes of capacity into the future. So RRAM array can be used to perform this in-memory matrix vector multiplication operations based on the Kirchhoff's law, right? So the computation itself is analog, and therefore it is quite energy efficient. But because the analog signals are typically more vulnerable to noises, and in order to have a robust communication with the rest of the system, one typically would put a digital to analog converters and analog to digital converters at the two ends of the array. Right. So now, assuming we have this very dense RRAM computing memory arrays, we can actually put multiple of them onto a single chip, right? And then we can essentially map all the neural network weights onto this computing memory arrays. And during the inference, the weights will just stay here, and we no longer need to fetch the weight from an external memory. So we call this a weight stationary architecture, and this can completely eliminate the memory access for these weights, and therefore it can eliminates all the latency and energy consumption associated with that. And we can really imagine an architecture where the weights of different layers of a neural network being mapped to this different RRAM subarrays, and by having a highly pipeline design to exploit this model level parallelism, we can realize a design that has ultra high neural network inference throughput. Right. So due to this great promises, and also due to the process of fabricating RRAM on top of CMOS getting more mature, so at a time we really saw a lot of progress in this field, right? So there were a growing number of RRAM computing memory test chips during the time, right? However, so most of the work at the time focused primarily on improving the energy efficiency. But many times this gain comes at a cost of the versatility and the accuracy of the chip. And most of the AI benchmark results at a time were at least partially simulated in the software rather than fully measured on the hardware. And as we'll talk about later, there's actually a big gap between the two. And the reason is that it's very easy to overestimate inference accuracy through the software simulation because it's very difficult and very challenging to accurately model all the hardware non-idealities presented in these analog computing blocks. And finally, so most of the tasks demonstrated at the time were limited to either simple data sets such as MNIST or a single type of neural network such as multi-layer perceptrons. So here was sort of our attempt to advance the state of the art at the time. So our work was published at Nature about 2 years ago, and this is really a collaborative effort between Stanford, UCSD, Tsinghua University, and University of Notre Dame. So the paper presents this chip that we named NeuRAM. So it consists of 48 RRAM computing memory cores, right? And here are two very nice photos of the chip. And from the photo, you can clearly see the 48 core design. So this chip is about the size of your fingertip, and it includes a total of 3 million RRAM devices. So this is a cross-sectional TEM image showing the monolithic integration of the CMOS and the RRAM. So the bottom transistor and the full layers of the metals were fabricated using a commercial foundry 130 nanometer process. And then the RRAM and metal 5 was deposited on top of the metal 4 using a research lab process. So it was really fabricated in two different foundries. So with the new RAM, we're trying to simultaneously address the three fundamental challenges of a RRAM computing memory chip: the energy efficiency, the reconfigurability, and the inference accuracy, right? So the energy efficiency of these analog computing blocks by itself could be quite high, right? But many times it was bottlenecked by the peripheral circuits, such as the analog to digital converters, right? And in terms of the reconfigurability, programming these RRAM devices can be much more energy consuming and also much slower compared to reading them, right? So we want to avoid reprogramming them during the inference. And this essentially make us lose the runtime reconfigurability of the array. And finally, this analog computation is susceptible to various device and circuit level imperfections, which might degrade inference accuracy. And importantly, these three aspects of the design are not independent. So many times the improvement of one will comes at the cost of the other two, right? And so this is really a fundamental design trade-off that cannot be addressed by an isolated improvement on any single layer of the design. So our approach to this challenge is really a full stack code design, all the way from the device and circuit to architecture, system, and algorithm. And this results in this neuron chip that can simultaneously advance the state of the art on the energy efficiency, reconfigurability, and inference accuracy at the same time, right? So it achieves the highest energy efficiency among all the RRAM computing memory chips at the time. And the chip was reconfigurable, and we actually got measurement results across diverse neural network architectures. And it also achieved comparable accuracy to software models quantized to 4-bit across all these different workloads. Right. So next, I'm gonna share several key innovations behind this design. So due to the time, I will only going to focus on the energy efficiency and the accuracy aspect. So typically, when people talk about these Kirchhoff's law-based computing memory, one would think of sending in voltage to one end of the array and measuring a current at the other end, right? And this is what most computing memory chip did at the time. However, this output doesn't have to be a current. It can also be voltage. And here we actually going to show that sensing voltage, it could actually be a better option in terms of both the energy efficiency and the throughput. So here's how a conventional current mode sensing works, right? So you would have these arrays where with this horizontal bit lines and vertical source lines, and also these horizontal word lines connecting to the gates of this 1T1R, right? And you would start by driving all the bit lines to a read voltage, and then clamping all the source lines to a reference voltage. So there will be a constant voltage drop VRead minus VREF across all the RRAM devices. And when the inference starts, you would activate the word lines with the one input, right? So that the current will start to flow from the corresponding bit lines to the source lines. And then the output of the the matrix vector multiplication will be sensed on the source line current, right? So this approach is a very intuitive, but it actually has several main shortcomings, right? So first of all, during this analog to digital conversion, there will be static current flowing both inside the array and inside the column peripheral circuits, right? So this can actually consume quite some energy because this current will need to present in the array for some time. And this is because the ADC's latency would grow with the bit precision. And for most of the neural networks, it requires more than 4-bit for activations in order to reach a high inference accuracy, right? So having this static current flow inside the array for extended period of time leads to high energy consumption. And at the same time, in order to deliver the high throughput of computing memory, you want to activate as many rows as possible in a single cycle, right? But that also leads to very high current along each of these source lines. And in order to sync this current at the column peripheral, you have to use very large transistor devices, which would actually create a lot of challenge to pitch match the peripheral with the very dense RRAM array. And therefore, one typically would share these peripheral circuits across multiple columns and then do time multiplexing, right? In other words, we cannot simultaneously achieve a high row parallelism and a high column parallelism. So the peak throughput is limited. So to address both of these issues, we propose this open circuit voltage mode sensing, right? So we would start by pre-charging all the source lines to the reference voltage. And then we would drive those bit lines with a 0 input to the reference voltage, and those bit lines with 1 input to Vref plus Vread, right? And then we would activate all the word lines while keeping all the source lines floating, right? And then while the word lines is on, all these source lines gonna start to settle towards a voltage that is equals to the weighted average of the voltage driven on the bit lines, right? Where the weights are the RRAM conductances. And we would turn off all the word lines immediately when the source line voltage settles, right? And this voltage will be retained by the parasitic capacitance along the source line. So finally, we would sample the charges from the parasitic capacitance along the source line to a sampling capacitor located within the column peripheral circuits, right? And we will use this to perform the analog to digital conversion. One thing you might notice is that the results does not exactly equals to matrix vector multiplication results. So it has this additional denominator term that is equals to the sum of all the conductance along a column. So this is not a problem because we can pre-compute this value before the inference and then multiply it back in the digital domain after analog to digital conversion. Right, so we experimentally verify this voltage mode sensing scheme, and here we can show that the measure results and the ideal results have a good agreement. So compared to the current mode sensing, where the static current keep flowing inside the array during the A to D conversion. So in this open circuit voltage mode sensing, the array can be turned off immediately when the source line settles, which in our design takes about 2.3 nanoseconds, right? So compared to the state-of-the-art work for implementing a current mode sensing at a time, this design achieved a 3.6x reduction in energy spent within the array. And this is really the key behind the higher energy efficiency of the neuron chip. And in terms of the throughput, because now these column peripheral circuits no longer need to sink very large current. So we no longer need to use very large transistors. In other words, now we can simultaneously turn on multiple rows and turn on multiple columns without a need to do time multiplexing, right? So the total throughput is a lot higher. we implemented such a voltage mode sensing scheme into this reconfigurable neuron design. So I'm not going to go into the details of the design, but from a high level, this neuron implements analog to digital conversion with a variable bit precision from 1 to 8 bit. It also implements common activation functions such as ReLU, sigmoid, and 10H. So using this design, we measured the energy efficiency of the chip, right? So the neuron can consistently deliver a lower energy delay product across variable input bit precisions compared to other RRAM computing memory chip at a time, despite being fabricated at a older technology node. Yeah, so next I'm going to talk about several techniques that we use to deal with the non-idealities and to improve the inference accuracy. So there are various kinds of non-idealities, both on the circuit and then on the device level, right? So first, all these wires and transistors have finite resistance, so there's IR drop. And in ideal world, this RRAM can be programmed precisely and can retain the value being programmed. But in reality, there are conductance relaxation. So we see the programmed weights actually spread out quite a bit. And of course, this ADC has limited resolution, so it will suffers from both the discretization and the clipping error. And finally, for this voltage mode sensing, it is susceptible to capacitive coupling, and so there you can observe a shift in the measured output. So the first technique that we use is called non-ideality aware model training, right? So the idea is very intuitive. So essentially, you try to model some of these key non-idealities during the neural network training, such that the model learn to combat these non-idealities, right? So for example, you can inject noises that emulate the RRAM conductance relaxation distribution into the weights. And you can quantize the input and the output of each layer to emulate the DAC and ADC discretization. So this very simple idea actually worked pretty well, right? So here we see that on the CIFAR 10 image classification, without a technique, the accuracy dropped all the way from 88% to 25%, right? But by introducing the technique, the accuracy can be recovered to 86%. But I have to point out that all these results shown so far are obtained from our software simulation. But the moment we actually go into the hardware measurement, we actually observe another 2% accuracy drop, right? And this is what I mentioned earlier. So it's very hard to get this complete equivalency between the software simulation and the hardware measurement in these analog computing blocks, right? And this is because it's very challenging to model all the non-idealities very accurately, and so that these non-modeled ones essentially contribute to this additional, accuracy loss. And to address this challenge, we came up with this chip in the loop progressive model fine-tuning technique, right? So the idea is really to bring the chip measurement into the training loop and let the neural network learn to compensate for the non-ideal computation, right? So we would start from a baseline model. And then we would program the weights one layer at a time. And then we would perform inference of the training set up to that layer. And then we would collect the output from the hardware. And then we would use this output to fine-tune the remaining layers that are still training in the software, right? So the idea is that the remaining layer will adapt such to compensate for the non-ideal computational results from all the previous layers. And then we would keep repeating this process until all the weights from all the layers are programmed onto the chip. Right. So here is a plot showing the efficacy of the readouts. Right. So each point here represents a new layer being programmed onto the chip. Each point is evaluated by running the inference up to that layer, and then running the remaining layers in the software, right? And we can see that at each layer, some of the accuracy drop could be recovered, and the final cumulative improvement is about 2%. So by combining these two techniques, so we measure across a diverse set of tasks, including MNIST and Cipher-10 image classification, voice command recognition using LSTM, and image recovery using an RBM. And on all these four tasks, the measure results, which was represented by this red bar in the middle, can be comparable to a software model that is quantized to 4-bit. Right. So in summary, this neuron chip, the goal was really to simultaneously address the three fundamental design considerations, the energy efficiency, reconfigurability, and inference accuracy, through an approach where co-optimize across this entire design stacks, right? And finally, I just like to share a little bit about my view of so where we are right now, and how to move forward, right? So apparently, Neuron is still just a research test chip, and there's still a very long way to go till this technology can truly be commercialized, right? So first of all, the device technology still needs to be largely improved, right? So there's still a big question mark there, whether this RRAM device can ever reach a DRAM level density, which I actually believe is very important in order to stay relevant to this ever increasing model size. We're looking at this gigabytes or hundreds gigabytes of big transformer models today, right? And of course, for these analog computing, it's still a very big, a very challenging task in terms of its robustness against both of these non-idealities and the PVT variations, right? And in order to overcome these issues, the additional circuits being introduced could lead to so much overhead that might completely overshadow the benefits of this analog design, right? And then on a system level, this 100x or even 1000x energy efficiency benefit brought by the analog computing could be overshadowed by could be reduced to 2x or even 3x if the system level energy consumption got dominated by other components, right? And finally, we really need a computing model that can essentially make these underlying hardware transparent to all the software developers, right? So the software developers, they can still write their PyTorch code, and their neural network model can just be seamlessly deployed onto this hardware, right? And therefore, to really get there, I think there still needs to be a lot of effort, collective effort from this entire community. Right. So finally, I'd like to thank all the sponsors of our research. Yeah, and I'm happy to answer any questions. Thank you.
Right. Thank you very much, Weier, for your nice presentation. Let me stop the recording first.